Welcome to the next video in a course in real analysis. Here we're discussing solutions to the exercises introduced in the video on orders. So for this first exercise, we are going to find all partial orders on the set AB and then decide which are total orders. So for all partial orders, we're going to have to satisfy reflexivity, but beyond that, you don't really have to have anything. And so this counts as a partial order, right? If you check antisymmetry and transitivity, they both hold in a kind of trivial way. And in fact, even here, right? So if all I do is add one extra comparison making A pre-seq B, then this will still satisfy, of course, reflexivity. And then if you check anti-symmetry and transitivity, they are still satisfied by this example. And also if I put things in the other order. Now, which of these are total orders? Well, here there is no comparison between A and B. And so this one is not total, it is only partial, but the other two are total orders. So now moving on to the second exercise where we're going to show some basic properties of the strict or precedence relation. We're going to show that it is reflexive, antisymmetric, and transitive. So to get started, I think I said irreflexive. I think I said reflexive, so irreflexive. So to show that it is irreflexive, then we'll pick an arbitrary element out of our set and show that the relation does not hold from this element A to A. And of course, part of the definition of A precedes A is, I'll just write out this part, although that's not going to be relevant here, but that is part of what we mean when we say that A precedes A. But the other part is that A would have to not equal A, because that's another part of strict precedence. Well, so that is just clearly incompatible with A equals A, and so we cannot have that A strictly precedes A. Okay, moving on to antisymmetric. Let's suppose that the relation, or sorry, not antisymmetric, asymmetric. Let's suppose that the relation holds in one direction, so A precedes B. And now we're going to try to show that B does not precede A. So to get started on this, well, since A precedes B, then A precedes, precedes or is equal to B. That is our partial order. And also baked into the idea of strict precedence is that A is not equal to B. And let's just note what we are currently trying to do. We're trying to show that the relation does not hold in the opposite direction. So we are currently trying to show that B precedes A does not hold. So for that purpose, we'll go ahead and assume that it does hold and try to derive a contradiction so that by proof by contradiction, we'll know that this is not true. Okay, now from the assumption for contradiction that B precedes A, then B must pre-seq A, because this communicates both pre-seq as well as not equal to. But in any case, so right, it is immediate from definitions that precedes implies pre-seqs. So okay, therefore, by the anti-symmetry of the pre-seq relation, right? Because, we now have that A precedes B, B precedes A, anti-symmetry delivers that A is equal to B, but that is immediately in contradiction with what we've earlier derived, which is that A does not equal B. So since a contradiction follows, then from the plan all along, the negation of this statement must be true, and that shows anti-symmetry. Okay, let's move on to transitivity. So let's assume that A precedes, or sorry, yeah, precedes B, B precedes C, and we are trying to show that, and here I'll just make a little note off to the side, we're trying to show that A precedes C directly. Now, certainly the transitivity of pre-seq has to be a nice way to approach this problem. So let's try to involve that. Well, certainly, again, since strict precedes implies pre-seqs, then we can go ahead and infer that. We can infer B pre-seqs C, and then by transitivity of pre-seq, we can say that A precedes C, but we still need to show that A is not equal to C. Then we could actually say that A strictly precedes C. So for contradiction, let's go ahead and assume that they are equal and try to derive a contradiction. So if they were equal, now, look, we already know from earlier that A precedes B. But if A is equal to C, then we could fill in A here and say that B must precede A, right? So that you have the relation holding in both directions. We know by anti-symmetry that that implies A is equal to B. And then we would have, well, I mean, that is kind of immediately a contradiction. We know this was an assumption of the problem, and it implies directly that A is not equal to B. So having also obtained that A equals B, we have our contradiction. So the proof by contradiction is complete, and we can infer that A is not equal to C. Since A is not equal to C, then the strict A precedes C is true, which concludes the demonstration of transitivity as desired. Okay, let's move on to exercise 3, where we're going to show by an example that A does not precede B is not the same thing in a poset as B precedes A. Okay, so to show this, we're going to come up with an example, and certainly it's got to be an example, right? I mean, if later on we're going to show that it is true in a totally ordered set, then certainly the example must hinge on this whole incommensurable sort of idea. So we're going to get an example where some two things are incommensurable. So let's go ahead and take the set of 1, 2 and the singleton set 2. And we have that if we identify the singleton of 1 with A and the singleton of 2 with B, then we have in this example that A does not strictly precede B, in the sense that A is not a strict subset of B. But also we don't have the other way around with pre-seq, right? We don't have that the singleton of 2 pre-seqs the singleton of 1. So here we have an example where the failure of A precedes B does not necessarily entail that B precedes A. So there is our counterexample, and now we'll move on to the proof. So let's now assume that we have a totally ordered set and show that they are equivalent. We'll first approach the left to right direction, meaning that we will take some two elements A and B such that A does not precede B, and show that the reverse pre-seq does hold. Okay, so in order to do that, then we must have, right, so by definition of negating this, and keep in mind that A precedes B holds if and only if A precedes B and A is not equal to B. So if this is not true, it must be because either this is not true or because this is not true. And so, the negation of this clause is that A is equal to B, and the negation of this clause is A does not pre-seek B. So this disjunction follows from A does not precede B. So let's approach the rest of the proof by cases. So suppose that the former case holds, right? If A is equal to B, then by reflexivity, right? Because A and B are equal, you know, A preseeks A, of course, but if A is equal to B, then B preseeks A merely by substitution. And there we have, you know, what we're trying to prove. Keep in mind what we're trying to prove is this B preseeks A in this case, and we have it under that assumption. So let's move on to the other assumption. So consider the possibility that A does not preseek B, and then by totality, right? So this is where the total ordering property becomes crucial. By totality, it must be that B preseeks A. And again, that was the very thing we were trying to prove this whole time. And so we're done now with the left to right direction. Let's move on to the right to left direction. So we're going to suppose that B preseeks A. We're going to try to prove, remember, right, the goal is, you can see down here at the end, that the goal is to show that A does not strictly precede B. So let's assume for contradiction that it does, right? Let's assume for contradiction that A precedes B, and from that it follows that A preseeks B, and then putting that together with B preseek A, we get that A is equal to B. But again, part of what it means for A to precede B is that A and B must not be equal to each other. Since that is in contradiction with what we just showed, then we must know that our assumption, right, our hypothesis for contradiction is false. And so we conclude our proof. Okay, and let's move on to solution number 4 for problem number 4. So we have this set, and the, you know, these natural numbers are ordered by divisibility, and we're going to show that this is a partial but not a total order. And so to get started on that, you know, somewhat trivially, you know, you can prove it to yourself if you want, but I think it's pretty obvious that every number divides itself. And therefore, this relation between the natural numbers is reflexive. Let's move on to anti-symmetric. So first, before getting into it, I want to just note that if A divides B, then A is less than or equal to B. And so now consider, you know, the hypothesis that A divides B, right? The relation holds in one direction, and also B divides A, so the relation holds in the opposite direction. Well, then we have both this inequality on natural numbers and this inequality on natural numbers. We know from all of our knowledge of natural numbers that these two inequalities must imply that A is equal to B, and that is exactly what we wanted to show for anti-symmetry. So all that remains at this point is to show transitivity, and although this is a common exercise in discrete math, I'll go ahead and step through it. So let's assume that A divides B and also B divides C. And so by definition of what that means, right, the very definition of divisibility is the existence of some integers, because I've specified that they're positive, and that is true, although that's not part of what the definition means, so we don't need this, but in any case, it is true, but it's just not necessary for the proof. So anyway, such that AK1 equals B, right? So we know that because A divides B, then this choice of K1 must exist such that AK1 equals B. Very definition of divisibility. And likewise, BK2 equals C, very similar idea. And now let's talk about relating C directly to A. Well, if C is equal to BK2, and then B, we have an equality for that, so I could substitute B in there, And so instead of having BK2, I instead have AK1K2, because AK1 is equal to B. Rearrange so that we explicitly group the, sort of multiplier away from A, or aside from A, however you want to say that. But in any case, this very picture of C equal to A times some integer is the very picture of A dividing C. And since A divides C, that shows transitivity. Since we have shown transitivity, we now know that this relation is a partial order. To see that it's not a total order, all we have to do is observe that 3 does not divide 4, and also 4 does not divide 3. There are many other examples that you could have picked for this, but I just chose that one arbitrarily. But there you go. So since some two elements, namely 3 and 4, are incommensurable, then it is not a total order, and the proof is complete.